As I confessed in a previous video, I have serious trouble growing crystals. So for Valentine's Day, which is a very special holiday indeed, I decided to give crystal growing another try. You see, Valentine's Day is my birthday, and I don't want to let another year go by without honing my crystal growing technique. This activity is designed for small children, so surely I should be able to complete it successfully, right? The instructions I'm following were clearly written by a non-chemist, so I glossed over them. A saturated solution of sodium chloride in boiling water. I'm even using lab-grade sodium chloride instead of from the cupboard. Construction paper hearts, and a tray to let the solution evaporate and crystals to grow. Fine. Easy enough. I even measured out how much salt should dissolve in the amount of water I'm using. So here we have it, a saturated solution of sodium chloride in boiling water. Well, it was boiling a moment ago. Hindsight mistake number one. There's way too much undissolved salt in there. That's going to be a problem. Now for the paper heart. Yeah, heart-shaped tray. Overkill. I know. I prepared this and several more hearts off camera. Because, seriously, who needs to see a grown man cut out paper hearts? The piping hot salt solution is getting poured onto the paper heart, and I seem to have avoided pouring out the excess chunks, so good for me. I moved this to an area in the lab that's out of the way. That was challenging. Moving a boiling hot, liquid-filled, shallow tray. 50 feet. It was challenging. There was an awful lot of salt left, so I decided to add more water and boil it up again. This way my other paper hearts can get treated too. And here they are, in an obscure corner of the lab. Crystals are already starting to form, and it looks like there will be lots of little crystals instead of a few big ones like the example photo showed. In the meantime, there's another crystal growing experiment I've been avoiding. Here's a solution of sodium borate, aka borax, that's been cooking for a little while. At room temperature, saturation is about 4 to 6%. At boiling, 116% if my math and merc are correct. Since that would take far more borax than I have in stock for the volume I'm hoping to work with, I opt for a 25% solution instead, and a few other shortcuts along the way. Once the solution's prepared, I take the beaker to the same obscure corner of the lab and finish the prep there. This is a classic experiment where you put formed pipe cleaners into the solution and crystals grow on them. I made this lovely specimen and secured the ends with some copper wire. This way it can dangle in the solution and avoid the walls. It's going to be great. I do have to adjust the height of the wire a little bit to get everything covered, but that's minor. I made a few more chenille hearts in a few different colors, including these handsome intertwined hearts. Hindsight mistake number two. Every set of instructions I've ever read on this experiment say to avoid touching the walls of the container. Everything I know as a chemist says one at a time, but my impatience and unwillingness to use a kilogram of borax has set me up for a spectacular failure. And I knew it as I dropped each one of these things in there. So that's something to overcome if I ever plan to grow nice crystals. Be patient. So while these do their thing, let's move on. Many birthdays ago, I got a chemistry set that this curious flower had in it. Not surprisingly, I still have the flower. But surprisingly, I managed to find it without much trouble. All we have to do is add a little splash of ammonia to some water, and then give the little flower a quick dunk. As if by magic, our little white flower has turned pink. Yay! The little silk flower has been impregnated with phenolphthalein, and so the ammonia turns it pink. What's more, if you shake it around a little bit, you can get some of the ammonia to escape and the color to fade, all while spraying chemicals everywhere. It's great fun. Your date will love it. so long as she doesn't mind the insanely romantic aroma of ammonia. After just a few minutes, most of the ammonia is gone and the flower goes back to white. But all of this got me thinking, can it be done with real flowers? Well, it seems like as good a time as any to find out. Daisies and carnations are supposed to be the best at taking up color, so I've chosen those for this experiment. And this is an experiment. I have no idea how this is going to turn out. I'll start with the carnations. I'm going to cut them down to a manageable size and remove the excess foliage to prevent rot. Hindsight mistake number 3. Since this experiment only lasted 2 or 3 days, the foliage probably should have stayed. It only compromised the stem, and nothing even thought about rotting for the short duration of the experiment. The next thing I'm going to do is cut the stem up from the bottom so I can split it into 3 sections. Hindsight mistake number 4. I should have left it at 2. Now I have 6 test tubes all full of very warm tap water. Flowers take up warm water quicker than cold water. Nice to know. To each, I'm going to add way too much food coloring. This is a good time to play around with coloring flowers with just standard food coloring, and it turns out to be a good move for comparison purposes. Here's a good shot of the stem in 3 pieces. Each piece will go into a different colored test tube. Eventually, I get the flower to stay up on its own and move on to the next part. Now I can start making color-changing flowers. Hopefully. I have 2 beakers of warm water, and to the first I'll add a few milliliters of strong 2.5% phenolphthalein solution. Hindsight mistake number 5. Phenolphthalein is almost completely insoluble in water. I need a better solvent. I don't think straight up alcohol would be good for the flower, but water's not going to cut it. Oh well, I'll try it anyway. To the next beaker, I'll add a 1% solution of rhodamine B. A lot of it. A whole lot of it. And finally, tonic water. Tonic water contains quinine, which fluoresces under UV light. This was suggested in a few different sources, so it should make a glowing flower with no problem. Now it's just a simple matter of trimming the stems and removing the leaves, which again probably should have stayed on there. What I probably should have done with the phenolphthalein was briefly soak the flower in the alcoholic solution and then let it dry, just like how the silk flower was made. If it is insoluble in water, of course it's not going to be taken up in an aqueous system. That's a continuation of hindsight mistake number 5, just in case you're keeping track. The daisies are up next, and I basically do the same thing for all of them. I sliced off the individual blooms, which gave me more flowers than I actually needed. So once I duplicated all of the conditions I put the carnations in, why not go crazy? From the left, we have rhodamine 6G, phenol red, fluorescein, bromethymol blue, crystal violet, and bromphenol blue. A daisy's going in each one of these. Here's the lineup. As you might be able to tell from the dark shadow, it's nighttime. I'm going to leave these overnight and see how far they get by morning. The beaker all the way at the right is untreated. That's just water. Right before bed, I'd say about an hour and a half after I left them, I noticed that the blue food coloring and red food coloring were already working on the individual daisies. I threw those in as an afterthought in case the rainbow flowers didn't work. Good thing I did. Here we are the next morning, and wow, those rainbow daisies look great. It's obvious that the food dye works the best. There's also noticeable color on the bromphenol blue flower in front all the way to the right. Everything else is pretty boring. I left it alone all day, and the colors developed more. I was curious to see if the fluorescent dyes worked at all, so you can clearly see which test tubes are glowing, but the flowers within them show no signs of fluorescence. Here we are the next morning, and the rainbow daisies are looking pretty sad, probably on account of their stems being sliced. The rainbow one's not bad. There are even some petals that have a green color where the blue and the yellow mixed. The red and blue one by themselves that remained intact are by far the best out of all of them. What I think is really neat is just how much water has been soaked up. Look at the red one. These were all the same level when I started. Out of everything else, it seems like only the bromphenol blue seems to have done anything, and that's not really all that much. Since now I'm filming during the day, I have to find another obscure corner of the lab that's actually dark enough to see if the fluorescent dyes did anything. And sadly, the answer's no. The quinine was supposed to be a sure thing, and there's absolutely no hint of fluorescence from the flower. The only things fluorescing are the stems that have been coated with the dye. It's kind of a letdown, honestly. The only one that has some hint of fluorescence in the petals is fluorescein. I'm going to leave it, the quinine, and the rhodamine B for another day, just to see if it's taking these things up a little bit slower. Back out in daylight, let's see about the color-changing flowers. I'm going to take just a single petal from one of the phenolphthalein flowers and see if we can get any reaction. It's pretty clear that, at least instantly, nothing at all happens. There's a little bit from my glove that gets on there, but that doesn't count. What about the bromphenol blue? Again, I'm going to take just one petal, only this time I'm going to put it into the left-hand beaker, which is vinegar. See what happens. You can see that the color of the bromphenol blue isn't very strong to begin with. And clearly there's no instantaneous reaction with this either. There's no immediate change with the ammonia either. Since a single petal didn't work instantaneously, why don't we try the whole dang flower and leave it in there for a second or two. Unfortunately, during this process, some of the phenolphthalein from the stem gets into the ammonia solution and gives it a pink color, but it's kind of a false positive. The flower petals themselves don't change at all. Now, with a larger beaker and some fresh ammonia, let's see what happens to the carnation. There is a slight color change, and it's turning yellow, which is not pink. It seems like there's some natural component in the flower to start with that's reacting with the ammonia to give a yellow color. I left it to soak for about a minute, and you can see that the yellow color is pretty pronounced. For comparison purposes, I got another large beaker, and I'll put some vinegar in this one. The ammonia solution I'm using is pretty weak, so the 5% acetic acid in vinegar will neutralize it completely, with plenty left over to keep the solution acidic. In spite of that, the yellow color does remain steadfast. Perhaps not surprisingly, the daisy that was in the phenolphthalein had pretty much the same non-existent reaction. Next up is going to be the bromphenol blue, and unfortunately, that also doesn't do anything. A few days later, the now very sad-looking fluorescent flowers are still not very fluorescent either. I tried all of the indicators, none of them had any reaction whatsoever. So the conclusion is, food dye works. period. Alright, let's head back to the other obscure corner and see how the crystals are doing. The borax didn't actually crystallize for more than 16 hours. It remained in a supersaturated state, and then all of a sudden there was this mess. We'll come back to that in a minute. The salty hearts did end up being small crystals, and that has everything to do with there being too much salt not in solution when they got poured. The red hearts are still a little bit wet, so I'll leave them to dry another day before the final assessment. At least there are a couple of decent sized cubic crystals on one of the hearts. After that extra drying time, the pink heart, which is office paper, is glazed nicely with salt. The red hearts, which are construction paper, stuck to the other paper as they dried. This one's a total loss. The one with big crystals looks halfway decent, but nothing like what was advertised. Let's refresh our memories. Alright, well, let's see if we can replicate that a little. Oh, here's a good crystal. And another. A few more. Now get that out of there. On second thought, let's just use the little crystals as dust. And actually, the stuff left behind is kind of neat looking. It's hard to tell on camera, but some of the dye got taken up by the salt. I don't think this is quite as wholesome as Himalayan pink salt, though. Now on to this thing. Geez, I can't even lift that out. I need to do a little surgery. Get in there. Come on, out you go. There. Ta-da! Well, this is interesting. Well, I'm just going to let this thing dry and then inspect the damage later. Well, it turned into more of a desk sculpture than an ornament, but it's not totally hideous, and at least I grew crystals. If I had someone to give it to this Valentine's Day, maybe I'd try harder, but I don't. One quick note about disposal. Even though these are water-soluble and relatively non-toxic salts, throw the extra crystals in the garbage rather than dumping them down the drain. There's no need overwhelming the system. Well, thanks a lot for watching. Happy Valentine's Day, and I'll see you in the next one.